In this lesson, we'll talk about Newton's first law, Newton's second law, force, and mass. Let's start off with Newton's first law, also called the law of inertia. Newton's first law says an object at rest remains at rest, and an object in motion continues in motion with constant velocity unless the object experiences a net external force. Let's talk about just the bold print portion of it right now. An object at rest remains at rest, and an object in motion continues in motion with constant velocity. Here we have two objects that are obviously at rest. And if we saw them move, we would very much expect there to be some reason or some cause for them to move. We would not expect them just to start moving all by themselves. So an object at rest will remain at rest unless a force acts upon it to cause it to start moving. Likewise, things that are in motion, like these mashed potatoes, I'm going to scoop them out of the bowl and get them going. And even though I stopped the spoon, the mashed potatoes kept moving. Only the force of the bowl, when they finally hit the bowl, did they come to rest or stop. Here's another example of an object in motion staying in motion. This is the Mars rover on the way to Mars. And here you see this is the portion of the trip where the spacecraft is accelerating towards Mars. And there's lots of good physics going on in this, but we're not going to talk about all of them right now. There's propulsion from the rocket engine that is a force that causes the spacecraft to accelerate. Now that you can imagine the spacecraft is moving through space and moving towards the direction of Mars. 7 months go by. An object in motion stays in motion. It's still moving. No forces, no rocket engines have been pushing it. It's just been moving at the same speed for 7 months. Now, as it enters Mars' atmosphere, although it's a thin atmosphere, it exerts a force on the spacecraft, slowing it down, changing its velocity. The parachute adds yet another force to slow it down even more. So Newton's first law is telling us that unless a force acts on an object, if it's at rest, it's going to stay at rest, and if it's moving, it's going to keep moving at the same speed. But let's take a closer look at this last part. Unless the object experiences a net external force. What does that mean, a net external force? And let's take a look at some examples. Here's an object at rest on the table. We've got the weight of gravity pushing down on the cassette, and we've got the support of the table pushing up. They're equal and opposite forces. Their effects cancel each other out, and so we say the net force acting on the cassette is 0. So there are forces acting on this cassette tape, yet it is at rest. It is not moving. So here's where we have to understand what it means when we say a net external force. So let's draw a diagram. Let's show the forces acting on the cassette. So there's gravity pulling down on the cassette. We call that the cassette's weight, and that is a force. If it weren't for the table, the cassette would fall to the ground. So obviously the table is supporting it with a force, and so we'll call that for now, we'll call that the force of the table. And we see that one is pointing down, one is pointing up. Forces are vectors, so the magnitude of these forces are the same, but their directions are completely opposite. So their effects cancel each other out, and we say the sum of the forces is 0. That's what we mean by net force. We're summing with vectors. The vector sum of all the forces adds to 0. And here's the mathematical way we'll show that. Sigma, standing for sum, the sum of the forces equals 0. Now if I push on it, it will slide across the table, and we know that sliding objects experience friction. Friction always opposes motion, so as it's sliding, the frictional force opposes the motion, and that's what slows it down. While I push on it, I'm pushing harder than the force of friction, so the net force is in this direction, and the cassette accelerates in that direction, and then it slows to a stop because the frictional force acts in this direction and accelerates it, or we say it decelerates it, as the cassette slows down. So let's take a look at the diagram of these two situations, while I'm pushing it and while it's sliding to a stop. So first off, let's take a look at while I'm pushing it. The force of gravity is still there, of course. The support force of the table is also still there, of course. But here's an important point. Forces on one axis have no effect on acceleration on the other axes. So here we can say my force of pushing is on the x-axis, but the weight and the force of the table are on the y-axis. So if I'm going to be looking at my acceleration and analyzing the acceleration of the cassette in the x direction, I really don't need to pay attention to these forces because they are in the y-axis and they have no effect. So I'm just going to dim them here. They're still there. These are not the forces we're concerned about right now. Okay? So let's look at my pushing force. There it is. I'm going to push on the cassette right there. We could draw it right there if we wanted to, but we choose to draw all of our vectors with the tail of the vector on the object. Remember, vectors are equal no matter if I draw it here or here. So I'm going to draw it over here. There's the force that I push on the cassette with. Now, I can slightly push on it and it won't move yet. When that is true, and I'm just barely pushing on it, that tells me that the frictional force and the pushing force are equal. How do I know that? Well, because the sum of the forces adds to 0 in the x direction, and the acceleration is 0. The cassette stays at rest. But as soon as I get this pushing force to be larger than the friction, now it's going to slide. And when I do the vector sum of these two forces, the net force will be to the left, and the cassette will start to move or accelerate to the left. Once I push the cassette and it starts sliding across the table, my finger is no longer in contact with it, so this force is gone. Now the only force in the x direction is that of friction. Remember, we like to draw the vectors with their tails on the objects. So as it's sliding across the tabletop, the net force in the x direction is just the frictional force. It is the only force in the x direction. So that net external force in the x direction will create an acceleration in the x direction. In this case, it will cause the cassette tape to slow down and eventually come to a stop as it slides across the table. So this frictional force is what causes the cassette tape to eventually come to rest. But what if we could, let's imagine we could take this frictional force and we could make it very, very, very small. Now the cassette would slide for a lot longer. Or if we chose some different objects, let's say, for example, we chose, instead of a tabletop, we chose an ice rink. And instead of a cassette tape, we chose a hockey puck. We know that hockey pucks slide very well on ice, and this small force of friction between ice and a rubber hockey puck doesn't cause it to slow down very fast, and it would slide for a very long distance. But I don't have a hockey rink in my classroom, so I have to use something that I do have. Let's do something fun. Another surface that we know is famous for being slippery is a banana peel. Let's try a little experiment with a banana peel where we take the peels and I'm going to cut them up and we're going to put them under the leg of a chair. No banana peels. Not very far. Alright, so I'm going to take my banana peel and I'm going to cut it into several small pieces. There we go. And now I'm going to take each of these pieces and I'm going to put them underneath this chair, under each leg of the chair. And now we've got our sliding banana chair.
Okay. Have a seat.
Okay, here we go. Whoa! Whoa!
Okay, here we go. And
Woo! Ah, this is great! All right, ladies and gentlemen. Turn these on. Not too bad.
all right.
All right.
All right.
Take two.
Let's talk about why Newton's first law is also sometimes called the law of inertia. So here's me pushing Tim on the banana chair. Let's change the situation a bit. Let's change the amount of mass or weight that's in the chair. So let's replace Tim with, say, a ton of bricks. If I did that, you would have a much more difficult time getting the bricks going, and additionally, it would be much more difficult to get them to stop as well. So a net external force causes velocity to change. In other words, a net external force causes acceleration. So that would be me pushing on the chair and Tim. But as we are going to see in Newton's second law, something else also comes into play. Not just how much is the force, but how much mass is there that is going to be accelerated. But before we look at Newton's second law, let's look at a little bit of some examples of inertia. In this example, we see a very large ship coming into the dock. Now, a large ship obviously has a lot of mass, so it has a lot of inertia. You can think of inertia and mass as being synonyms of one another. So as the boat is coming into the dock, remember boats don't have brakes, they just have to rely on the frictional force of the water that's in the way to slow the boat down. So that's the force. The net external force acting on the boat is the water opposing its motion, the frictional force. But the ship has a lot of inertia, so that force does not slow it down appreciably, and you can see the result. Now let's look at something you're probably familiar with, kicking a soccer ball. A soccer ball has a given amount of mass and thus inertia. Now let's look at a sand-filled medicine ball.
Oh my gosh!
Much more inertia. Joking aside, inertia can have some very serious examples as well. Take this example here. We see a chair sliding, and the books that were on the chair keep moving, just as a person in a car will keep moving if they don't have their seatbelt on. So that's why you'll always want to wear your seatbelt in your car, because you have mass and you have inertia. Let's talk about Newton's second law now, also known as F equals ma. Let's see what it says. It says, the acceleration of an object is directly proportional to the net external force acting on the object and inversely proportional to the object's mass. So this equation right here is written in the form that supports the wording of Newton's second law. This force is in the numerator of this fraction, which means that if it goes up, the acceleration goes up. So they are directly proportional to one another. The mass is in the denominator, so if it goes up, this fraction as a whole will go down. So the more mass, the less acceleration. For example, the Mars rover. As Mars rover travels through space for 7 months, the frictionless environment of space, there is no force at all acting on the spaceship. So the numerator of this fraction is 0. So the acceleration is 0. The spaceship continued to Mars at a constant velocity. It did not accelerate. How about with the sliding banana chair? With the banana peels under the chair, the force of friction was much less than without the banana peels. So without the banana peels, the force of friction was larger, which created a greater acceleration, and the chair slowed down more quickly. And with the banana peels, the force of friction was much less, so the numerator here is a smaller number, so the acceleration is smaller, meaning that the velocity changed at a slower rate, and the chair slid for a longer distance and slowed down more slowly. How about the soccer ball? The soccer ball, compared to the medicine ball, has a much smaller mass, so being in the denominator, if the mass is smaller, the acceleration is greater, and that's what we saw. The soccer ball accelerated much more quickly, and the medicine ball, much to his dismay, did not accelerate very quickly. How about the example of the ship? As the ship crushed the dock, that certainly is a large force, but because the mass was so large, this fraction then was fairly small, and the ship did not slow down very quickly. Its acceleration was a small number. All right, so if we rearrange this equation, cross-multiply the m to the other side, we come up with a more common form of Newton's second law that says the sum of the forces is equal to mass times acceleration. And if we look at the units of that, units of force are newtons, units of mass is kilograms, and units of acceleration is meters per second squared. So this tells us that a kilogram meter per second squared is the same thing as a newton, which is a unit of force. And let's not forget, forces on one axis have no effect on acceleration on the other axis. So when we say the sum of the forces, we have to specifically say the sum of the forces in the x direction creates acceleration in the x direction, and sum of the forces in the y direction creates acceleration in the y. And if we were working in 3 dimensions, of course, we would also apply that to the z-axis. Let's look at one final video here that ties this all together in the weightlessness of space.
How do you measure the mass of objects in microgravity?
Well, we have a system here over, and it's located, unfortunately, down in one of the other modules, so I can't show you, but I can show you the basic idea here. The way it works is it uses a property of the fact that when you push on something with a certain force, it'll start to accelerate, it'll start to move. But the heavier, or the more mass it is, not necessarily the heavier it is, but the more mass it has, the slower it accelerates. So if something is twice as massive, it will only accelerate half as much if you push on it with the same amount of force. And that means that, for instance, if you have a spring pulling on, you can measure how fast it starts to move, and using that, figure out what its mass is. And I got a little demonstration here. Actually, it uses something, a little slightly different concept, but let me first show you one thing here. And this is just a tape measure, a plain old ordinary tape measure like you might find in a hardware store. And it retracts automatically. Basically a little spring. But what I can do is show you that if I attach this to something and then release it, the greater the mass is connected to this, the slower it accelerates. Let me show you. What I've done is just tape the tape measure off to this panel over here. I'm gonna pick my feet up and let this thing go, and I'll show you how fast it pulls me towards the wall here. You can see it's fairly slow because spring is not very strong. So now what let me do is I'm going to lock this thing off, and I'm going to attach to it something which has much less mass than me. This is just a roll of gray tape. You can see that accelerated much faster, and the reason is because it's much less massive than me. You can use that principle to measure the mass of objects. Now, what we do actually over in the with our measurement device, we use basically the same principle, but there's a little more accurate way to measure it, and that basically makes use of the fact that if you have a spring pulling on something, it's going to pull on something just like this tape measure did. But what it will do is if your spring has a center point, it will actually go past the point and swing back and oscillate back and forth. And so what I've done here is I've set up a little demonstration. I've strung a bungee across the corridor here, and it's basically something like a spring. If you pull on it, it bounces back. Well, what I'm going to do is pull on it, and I'll show you that, and then let go with my feet, and I will move back and forth, and you can see that I will move back and forth at a certain speed. Now, if I put a lighter object on there, the spring pulls it quicker when you let go of it, and then quicker when it pulls back the other direction, so it actually will oscillate back and forth at a much higher speed. And the speed at which something goes back and forth for the same size spring, if you put different masses on it, is going to depend upon the mass of the object that you put on it. And that's something that the students can try at home. You can set up a small device in a box with a couple of springs and different masses, and you can show that this works. So let me show you here. You should have been able to see that I was moving back and forth, and it took about maybe 2 seconds to go to one end and back. What I've got here is a big wrench, but it may be a big wrench, but it certainly has much less mass than me. And let me attach this to the same thing, and we'll let go of it, and we'll watch how fast it moves back and forth. You see this is moving quite a bit faster. It probably took maybe maybe a quarter of a second, something like that, to go from one end and back and forth again. So, in fact, the apparatus that we have is a much better version of this. It's a finely calibrated spring, and it measures the frequency or the period, the amount of time it takes to go back and forth, very accurately. And from that, we measure our mass.
So here we go. And after about 4 calculations, we have a readout, 81 kilograms. A little more than that, 81.5 kilograms.